Hello everyone! I will return back to the English language videos with this, and we will talk about a little bit about OOP. I was so I so wanted to put a P in front of it, but let's not do that. So we will talk about OOP, and actually we will talk about this blog post that is quite new on the internet, I would say. I don't see the time on it, but I see it at various places, and there is a lot of talk about what OOP is, what subtyping, how the various things are for Gang of Four and so on and so on. But we will be talking about especially the performance claims that they are claiming about, because they claim basically they made a microbenchmark, and we will go back to that. We will also go back to the OOP topic a little bit maybe, but they also claimed a microbenchmark that virtual function calls in modern day and age basically doesn't cost you anything. And I cannot disagree more. And I also think this benchmark is misleading a lot. So what they are doing is that they are creating a Turing machine. The source is somewhere on GitHub. So I just went and checked it out. I have this on my machine here. And basically we will test it. But I already, for the first sight, just by looking at it, I already realized some of its problems of the micro benchmark, and we will talk about it, okay? So, I still see a lot of merit to this article, but don't jump to very fast conclusions when you see something like that. So, yes. First of all, I want to show you how the codes are. Like, there is a non-object oriented version. A non-object oriented version is basically a lot of switch case statements. It has more switch case statements, some functions, so basically structs and similar things. For the object oriented version, they also have a lot of switch case statements and stuff like that, so that's not really like OP, Cleancode, cultist code, but they consider this OOP because if you search in it, you find that there is virtual at 4 places. Like, that's what they say OOP is, and that's where they claim that virtual function calls are not to be worried about. Okay, so they made a abstract class of state machine with all virtual things, and it can reject or accept some kind of state, and it can get to the next state with the symbol read. And this they are running with a Turing machine, and the Turing machine is somewhere here. It takes a state machine pointer, so it can be any kind of state machine, and the band, like the Turing machine will work on this band. It has these bands to store data on. That's how the machine works. And they store this in the constructor and then run the Turing machine. So, what's the problem with this? What I see as a problem is that this is just a single C++ file, single file, everything, single compilation unit, and the single compilation unit, it eases the compiler very much. It can devirtualize anything. You don't need link time optimizations, link time between compilation unit, link time, devirtualization, whatever, which makes it very slow to compile in real cases and not often happens anyways. So if everything is just jammed into the same CPP file, yeah, maybe it doesn't count much because the compiler can optimize out everything, like the virtual function call will be not there. So that's my issue. And just look at this. Just look at this. We have this before. I took their little example, literally copy-pasted into Compiler Explorer. This is the OOP version. And it ran 700 milliseconds. Okay, that's great. That's something. The current will, on my machine, the current one will be running faster because the band became smaller. There has been a change on the GitHub. And I did this yesterday. So this is screenshot from yesterday when I tried it just by looking at this. And do you know what I was doing? Do you know what? This is the after. I just added this highlighted part, the attribute noinline, to the Turing machine constructor, and it became twice twice the time to run this application. 2 times slower. 200% slower. I cannot say it's more loader. So you can just look at your eyes. Like it was this 700 something. It became 1500 something milliseconds. Okay? 2 times slower just by adding this here. And okay, you can argue that why I am working against the compiler. Like, isn't it the point of the post, of the blog post, that current days the compiler can optimize these things? But listen, in a real world application, in huge code bases, the compiler will not be able to devirtualize your virtual cores. It is able in these very small, tiny microbenchmarks, but it's not able to do that in a big code base. Why I know that? Because I have been working on high-perf C++, but I couldn't use concepts which are like similar to Rust traits. Basically, just if someone knows that, with other bells and whistles, never mind. So it's a compile time construct, basically compile time interfacing, and I would be able to do it that way, that very optimized way, that every check happens only on compile time. But I couldn't because the project couldn't be updated to a faster, newer compiler. So I had to do it with an old-style way, with marking something virtual, but I myself ensured that the devirtualization optimization kicks in and happens. And it sometimes takes considerable amount of work to do that. You can get lucky, like in these small cases, but in real code bases, you need to kind of make an effort so to force the compiler not make this virtual function call. You might mark classes as final. You can maybe remove some of the codes from CPP files into header files, and so on and so on and so on. It's just a little bit of trickery. Because of compilation, you need boundaries and everything. And in huge code bases, if you turn on link time optimization, it can get very slow builds sometimes. So it's not always a solution. Anyways, let's do this on my machine just so that you believe me. Because this, I tried with an old GCC and that made things even worse. So yeah, this is 10.3, which is an old version. And today I will make it with a completely new version. I just put it back here because there will be a Hungarian version of this video too, with maybe some other kind of things. So I checked out the codebase here, git cloned. I did this git checkout blog version because for some reason the main branch is not the same as the blog, and it's not newer, it's older. Anyways, I did this, and it has these files. We have this runall.sh, and for some reason it already throws out a lot of errors. So I don't know if anyone tried this except me, because it has a lot of errors. What are those errors? It has this floor, log2 functions. Basically they didn't include something. So log2 is basically in CMAT. I guess they didn't include CMAT. Vim, I can do whatever these are. We have this vim-p benchmark Turing. Okay, it can be everything but CPP. That's all. We can also do the. I don't need. Actually, we opened everything. So we have the functional version. It needs C. What was it? CMAT. We also need this. Okay. Also need here. Also need here. Okay, great. With the tuples, we also might need tuple because I don't see it. I don't know what kind of compiler they are using so that this is working. Yeah, make tuple is not there. So basically, I need also tuple here. What kind of code is that in GitHub that doesn't even compile? So just doing runall. Now we can see it. So we have the OOP version without optimizations. It takes like 173 milliseconds. With optimizations, it takes like 25. Then there is like the this is with the one with tuples, because tuples, when the optimization is not turned on, they have like extra bells and whistles. With optimization is turned on, it's basically the same. And there is like no tuples. So basically this is the procedural code. With optimizations, without optimizations, it's much faster than both previous ones. And with optimizations, it's also much faster than both. Okay. This is what I'm talking about. You see, it's nearly a 2x faster. It would be 2x faster if this would be 28. So make another measurement, because one measurement is not a measurement. Look at this, how big it jumps. Now OP3 is like 31. And this is like 23. Okay, I'm recording video, maybe that's why I'm jumping. It's still faster. Make one more. Okay, it has like 19. It has 13. But its table looks like that just as it is from GitHub, immediately checked out from GitHub on my LS Highway, on my machine, which is basically this CPU. So on this CPU on Linux, it's already faster than having the non-virtualized code. But look at this. Look at how much other faster it will be. Okay, go to the OOP version and add the little. Where is the Turing machine? The Turing machine is here. Just add attribute. Noinline. This prohibits the program. What is that? The compiler to inline this thing. And just look at it now. It's now becoming 56. And look, we had a very fast run when my laptop was having a higher clock frequency and everything. So actually this became even worse than here, and I think it will be just like very stably worse. You see, there is not much variation if the compiler cannot do the devirtualization. Okay, there was a little bit of variation here, but now it's consistently even slower than the other variant that has the tuples. And this is the tuples. Okay? So just beware of microbenchmarking things, because it might be very misleading. I actually didn't like previously the terms like, oh, microbenchmarks are so misleading, everyone do it badly and so on and so on, so you never believe it. But my point is that if microbenchmarks are done by people who don't really know performance computing and didn't have like hyper coding experience a lot, maybe they have C++ experience and they can do a nice job there, but not really the high performing, then it can be very misleading. It can be extremely misleading. And there is one more thing. I want to talk about here, and I will just draw for this, because okay, where is this virtual calls happening? Imagine what is happening here. You have a Turing machine. It gets a state machine. This state machine will be the same while the Turing machine is running. It will not change. So this will be the same. The reason why the compiler could optimize that out, because they see that, okay, here's the main, we are making some kind of call to this test function, and this test function is here, and they make a program, and this program, which is a palindrome recognizer, is given to the Turing machine, and that's all when the Turing machine is ever constructed, nowhere else. It's basically nowhere else constructed, just like there in the test. So they totally inlined everything, and there were no virtual function calls at all. We measured nothing. We measured noise. We measured how well the compiler differently optimized just different code paths without even touching OOP kind of constructs. I mean, okay, yeah, technically you make OOP with virtual calls, but in these very little toy examples, it's not there. It's optimized out, you're measuring nothing. And what is palindrome parameterized? You can see it's a state machine. If I even write here final, you can even hint the I guess here. I actually don't know where. We'll just do the run. Yeah, it's there. So it should be even faster a bit, but not now because the, you know, we made it not possible to have this thing. So let's just delete this and make a run. Look how faster it became. It became much faster than the previous version without a final event. So we can still hint the compiler to make a better job, okay? I hope you are paying attention. Yeah, because, you know, now the compiler see that, okay, that's a final. There is no way that some can subclass that. So it kind of makes an even stronger hint that this pointer there, which is a palindrome recognizer star, it cannot be anything else than a palindrome recognizer. Then it looks at the palindrome recognizer, it sees it's a state machine, and the state machine then it checks like there is no other state machine than the palindrome recognizer. So we are helping the compiler from two sides, that the state machine only has one subclass, and it's the whole file, there is no other files, no other source code, it's a single source code, single compilation unit. So that helps the compiler, and the other thing that helps and it's from the main function. And the other thing that helps the compiler is that I added final. Okay. So yeah. Let's do it this way. And this makes it slow. This only just like one term of writing there. It's still slow, even though it's like it had a bit lucky run. Maybe I have the final still somewhere. Nope. Anyways, it became consistently slower than the real solution. And I want to talk about some other things. First of all, if you really want to check the OOP style code, you are not writing these switch cases. Do you know what you are doing? Cleancode style OOP, real object-oriented design, dry principles, and gang of four, and those kind of things. You don't do these switch states. Do you know what you learn? You learn that you should create a subclasses for this state. The state, instead of an integer, it should be like something like an object pointer, and it should have subclasses for these kind of cases. And the transitions should like return a new object for those kind of cases, and they should have properties with left and right and true and false. Guess how slow that would be, because it would be always jumping back and forth between cases and cannot have any kind of branch prediction, literally. Because it would be like all virtual function calls everywhere, double jumping, very bad cache locality, everything's scattered around the memory. Maybe I can do that. Maybe I will make another video where I will do this. Maybe in Hungarian language I will make an extended video where I will also do this. Then you can check it out. Anyways. And this is actually the best case for testing virtual calls. Because, why? Because the Turing machine, as I said, this construction only happens like very rarely, and you store the state machine. You store this state machine, you store in this variable here, and this variable basically, what it makes? It helps everything, because you are not jumping between different kind of objects that you would do if the switch case you would try to do an object-oriented way, which would be very slow. Because here, guess what happens? Imagine there could be multiple implementations of state machine, and this is like an API, a library. Then you also don't have the cross-link time optimizations and devirtualization anyways, because you need to create a static linkable object or maybe a dynamic linkable DLL or SO file. And just imagine that there are multiple state machines, but you create the Turing machine. This is the TM, and there is like a state machine 1, and there is like a state machine 2, and when that Turing machine gets constructed, we get the state machine, so it will be this as a pointer, and this state machine 2 somewhere have, just wait, somewhere has an object like a class description. This is SM2C, like the class. This is where the class, like static variables and stuff like that, class specific things, and the virtual function table and the virtual functions are living. And we have this V table here, virtual function table. We also have like one similar for SM1C for class. It also has a V table, like a virtual function table. And there is like a function here, F2, and there is like a function here, F1. And this V table points to F1, this V table points to F2, and this SM2 points to here, and this SM1 points to here. Basically no, these pointers are not real, but when we are using, sorry, they are real, Yeah, the V table is actually here, sorry, the V table is actually here. Anyways, I just fucked it up. But the V, yeah, instead of this, we have a pointer to the object. This should be not class but object. This should be also not the class and object. This should not exist also. But the V table is pointing to a function. Anyways, we make one jump and two jump to get to the function instead of actually having no jump at all in memory when it could be inline. Anyways, but when we are not changing between these two, we are not having a Turing machine that has one program and runs another program and runs a three program. Basically, we can maybe make Turing machines like an S to here, like a multiple, but that would contain an array of state machines, and it would try to basically parallelize them, like step one of the state machines, step the other, step the third, step the fifth and fourth, and so on and so on. So basically, we could do that, maybe with a vector or something, that would make the Turing machine always, and of course the corresponding bands also, that would make the Turing machine collection or whatever, one time used one of the kind of virtual calls and one of the memory addresses, this area, and the second time the other area. So that would make a very bad cache locality. But look at this. This is always cache local in this case when you are not changing the thing very often. This is why, for example, if you have, I will just delete this, if you have a something of type T vector, and T can be either A or B or C, that became G, but that I don't care. And you are having this as a vector with us A, B, C, A, C, B, whatever. So in completely random order, and for all of them you call, let's say, a draw function. Like it draws all kinds of objects, like these are types. All types of objects draws themselves to the screen. This is slow because not only there is a virtual function call, but here we are jumping to the things for the A. Here we are jumping to the things for the B. Here we are jumping for the things for the C, both in branch prediction and cache locality. Here again for A. Here again for C. Here again for B. So it's basically all kinds of order. But if we are doing on other style, like it should be like A, B, C, and only C from that on. So basically, if we are ordering by the type, we will always go to the same cache locality and same branch prediction and same and C and C and C. So basically, this is local, this is local, and this is local, and this is also why it's faster. Of course, it's not as fast as making a separate arrays for A's, B's, and C's and just calling them without virtual functions, but it will have optimization. So basically, here we are testing a very happy case because the state machine stays the same. It cannot change often. When OOP really becomes bad is when you are using virtual functions and it changes often. That's a different thing. That's very different. And even in this bad state, you can see that not having the OOP variant is actually faster. That's all it works. So I don't believe microbenchmarks, but that's it. Oh, and just one more thing. Just one more thing. If you go back to here, there are also other misinformations. I will not look at that, but basically they try to say that you are using OOP just by having data and code together encapsulated in one thing. That's not OOP, folks. It doesn't call that OOP. Like, they didn't claim languages who do that were OOP when OOP was on this heights. Now that OOP is crumbling apart and a little bit no one likes it, the tides are turning, they claim that you are doing OOP if you are doing that. But let's look at ADA. You see, object-oriented programming, they added because there was a model mostly won by sheer popularity in Java and C++ way, because this is what they do, runtime polymorphism or whatever. But before object-oriented was popular, some of the mechanisms and concepts, the other programming language even had it before. You see, they had packages. Packages had code, types, and data. And guess what? Many people made like abstract data types, like a stack with that. Okay. Packages, how they look? Look, packages. They have like private parts and public parts. It was not considered OOP, just modular programming, and they already had this. Look, they had even types, procedures, public and private, and all kinds of records and stuff like that. Even hierarchical packages. Okay, maybe that's not your taste of tea. They had generics in ADA. Look, this is before the ADA had OOP. They could have generic packages. Look, that they have like type D somethings. And records, like they had variant records which kind of look like tagged, tagged unions, which is basically very close to the Rust enums. And they can even like added constraints on that and stuff like that. So look, with variant record, use variant record, and they could like have binary operation plus, minus, and this was not OOP. Like they had OOP added later to this language, and a lot of other languages like Fort, let's say Fort words can have basically data and code together stored in the same word, because that's how they structure things, and it's not OOP whatsoever. So don't say to me that just putting data and code together it's OOP. No one really said that before OOP started to go out of fashion. So anyways, I will not talk about that a lot, but the performance part I was a little bit not happy about. Maybe there are other compilers. I had to run mine with G++ currently because I didn't have the GCC at the song at the moment. But anyways, it's kind of, it all hinges how much devirtualization happens. Okay, so and that's it. Look at the things, look at what's behind, and also learn about memory and how things work behind the scenes. Goodbye.